Hello, second semester students. So in the last video, I completely explained the concept of entropy and the disorderliness of a system. Today, I would like to speak about the change of entropy in a reversible and irreversible process. So what should be the effect of entropy in a reversible process and what is the effect of entropy in a irreversible process? See, change of entropy in a system, for example, in adiabatic process, I told in the last class, it remains constant. So, what is the effect of entropy in a reversible and irreversible process? Let us discuss clearly in this few minutes. Look at that. Consider a working substance which undergoes number of operations in between the points A, B, C, D and A. So here this diagram represents the Carnot's cycle, which is composed of two isothermals and two adiabatics. See, AB represents isothermal process, BC represents adiabatic process, CD represents another adiabatic process, and DA represents another adiabatic process. So look at that. Here the working substance is subjected to four operations, which is composed of two isothermals and two adiabatics. See here the working substance absorbs a quantity of heat at a temperature T1, an amount of Q1, and it rejects a quantity of heat Q2 at a lower temperature T2, and you can easily apply the Carnot's theorem. When the substance goes from A to B, it is an isothermal process. Here it is continuously absorbing heat. Because of that, here the gain of entropy is going to take place. That is, ds is equal to Q1 divided by T1, gain of entropy. In this indicator diagram, AB represents a increase in entropy. If you come to BC, I already told that it's an adiabatic process. Because of that, entropy here, it remains constant. No change in entropy in adiabatic process. Why? Because no question of heat is absorbed or no question of heat is removed from the system. So that is known as adiabatic process. There, in the last class, I clearly explained the change of entropy in an adiabatic process remains zero. Therefore, I will not count what is the change in entropy between the curve B and C. If you come to CD again, again it is an isothermal process. Because of that, change in entropy between the points C and D is an isothermal, but here the process took place in the reverse direction, in the opposite direction. So because of that, here the change in entropy will be loss. So here it is gain in the beginning, and the second isothermal curve represents the loss in entropy. So that is ds is equal to minus Q1 divided Q2 divided by T2. Q2 divided by T2. So here is loss of entropy, and when it goes from D to A, the change in entropy will be again an adiabatic. Change in entropy remains constant. So because of that, so here no change in entropy took place between D and A. So the total change in entropy in a reversible process that took place between the points A, B, C, D, A will be calculated like this. So that is ds is equal to Q1 divided by T1 plus minus of Q2 divided by T2. But from the theorem of Carnot or efficiency of a Carnot seat engine, it is possible to show that eta is equal to 1 minus T2 divided by T1. Similarly, eta is equal to 1 minus Q2 divided by Q1. It is possible to show that Q1 divided by T1 is equal to Q2 divided by T2. Therefore, the change in entropy in a reversible process ds is equal to Q1 divided by T1 minus Q2 divided by T2. Since it is possible to show that Q1 divided by T1 is equal to Q2 divided by T2, therefore ds becomes 0. That is, the change in entropy during reversible process remains constant, remains 0. So therefore, all thermodynamic process which undergoes a reversible process will have a constant entropy. But in a reversible process, irreversible process, the change in entropy will be always increases. The change in entropy in a irreversible process always increases. But change in entropy may be 0, change in entropy may be positive, it will never become negative. Change in entropy will never become negative. Therefore, change in entropy in a reversible process remains constant, and change in entropy in a reversible